Right now, more than 60% of the continental United States is bone dry, the worst spring drought ever recorded. Soil cracked open, rivers pulling back, over 1,500 wildfires already burning in Florida alone. You might think this is just a bad dry spell, a rough season, it will rain soon. Scientists say something far bigger is breaking underneath all of it. An ocean current the size of a river, running through every ocean on Earth, is slowing down. And when it stops, the rain doesn't just become rare, it disappears. We are going to cover how a wall of air locked out the rain, how farms collapsed in weeks, how the groundwater millions of people drink hit its lowest point in 15 years, and what a dying ocean current means for every city on the East Coast. If you find this important, like and subscribe. Now, let's start from the ground up. Sometime in early 2026, a farmer in northern Florida walked out to his field and found the ground cracked like old concrete. It was March. The wet season was still months away, but the soil looked like August in the middle of a heat wave. He hadn't seen rain in weeks. His irrigation system was already running at full capacity, and it still wasn't enough. That farmer was not alone. By spring of 2026, more than 60% of the continental United States had entered moderate to exceptional drought. That is the largest drought footprint ever recorded for the spring season since scientists began tracking it in the year 2000. Normally, droughts peak in late summer. The soil dries slowly over months. Farmers have time to adapt. Emergency systems have time to respond. This one didn't follow the rules. It exploded in the spring exactly when crops go into the ground, exactly when water demand spikes, and exactly when the country has the least margin for error. Fields that should have been wet from winter rains were already dusty. Streams that feed irrigation canals were running thin. And the heat kept climbing. The southeast got hit hardest. Florida, Georgia, the Carolinas, Alabama, states where people are used to afternoon thunderstorms rolling in like clockwork every summer day. That cycle broke. High pressure locked over the region like a lid on a pot, and the storms simply stopped arriving. By late April, nearly all of Florida sat under some level of drought. 80% of the state had fallen into extreme drought conditions. For a state surrounded by water on three sides, that number seems almost impossible. But the ocean being nearby means nothing if the atmospheric patterns that pull moisture inland have shifted. Over 70 weather stations across the country recorded their driest October in history back in 2024. Then winter arrived with less snowpack than usual in the mountains out west. Then spring came and delivered almost nothing. The drought had been building quietly for months. By the time most people noticed, it was already a record breaker. And the damage was already stacking up fast. Agricultural losses in the southeast crossed $3 billion. Livestock feed became scarce. Grocery prices started climbing, and underground water reserves that took thousands of years to fill began dropping at a rate that made water managers nervous. The Floridan Aquifer, one of the most important underground water systems in the country, hit levels it hadn't seen since 2011. 78% of the American population faced abnormal dryness by late 2024. That figure climbed higher through the following spring. Cities that had never worried about water restrictions started posting signs about lawn watering limits and car wash bans. The country was drying out, faster than the systems built to handle drought could keep up. But here is what made scientists genuinely alarmed. They weren't just watching a dry spring. They were watching a dry spring that matched patterns tied to something much larger happening in the ocean. Something that had been changing slowly for years. Something that most people had never heard of. A current, a massive, slow river moving through the Atlantic Ocean, carrying heat and rain across the entire northern hemisphere. And it was weakening. The next question was simple and terrifying. How fast? A regular drought gives you warning signs. The rain slows down over weeks. The soil dries gradually. Farmers watch the forecast, adjust their plans. and make hard decisions early. Emergency agencies activate. Water managers start rationing before the crisis hits. A flash drought gives you nothing. It arrives like a switch flipping. One week the ground holds moisture. The next week the heat spikes. The wind picks up. And the soil begins losing water faster than any forecast predicted. Within 10 days, fields that looked healthy start showing stress. Within 3 weeks, crops that took months to grow can be completely lost. Scientists classify a flash drought when soil moisture drops from normal to severe in a matter of weeks. The speed is what makes it so destructive. A slow drought lets people react. A flash drought outruns the reaction entirely. In the spring of 2026, flash droughts punched across the southeast like dominoes falling. A farmer in Georgia might have planted his crop on a Monday with confidence, watching a reasonable 10-day forecast. By the following week, a dome of high pressure had settled overhead. Temperatures jumped 8 to 10 degrees above normal, and the wind started pulling moisture out of the soil at double the normal rate. The forecast that looked safe 2 weeks ago was now useless. The mechanism is straightforward once you understand it. Heat is the engine. When temperatures climb far above seasonal averages, the air gets hungry for moisture. It pulls water out of soil the same way a hot oven dries out a piece of bread. The faster the heat builds, the faster the soil loses what little water it holds. Once the top layer dries out, the plants can't reach the moisture below. Roots stress, leaves curl, growth stops. In a flash drought, this entire process happens in the span of time it takes to plan a response, order emergency water resources, or even file a disaster declaration. And then the fire risk arrives almost immediately. Dead and dried vegetation becomes fuel. In a normal drought, this buildup happens over months, and fire agencies have time to prepare. In a flash drought, a landscape can go from green to fire-ready in under a month. That is exactly what happened across Florida and neighboring states in early 2026. The vegetation that had survived a cold snap earlier in the year was already weakened. The flash drought finished it off quickly. By the time fire season officially began, the fuel was already loaded and waiting. Farmers had almost no recourse. Crop insurance systems are built around slow-developing disasters. When losses happen in weeks, the paperwork often takes longer than the growing season itself. Some farmers simply walked fields they had already planted, watched the damage accumulate, and began calculating what they could afford to lose. The $3 billion agricultural loss figure for the Southeast didn't build slowly. A significant chunk of it arrived in weeks, not months. Flash droughts were already growing more frequent before 2026. Climate data showed they had been increasing across the central and eastern United States over the past 2 decades. Scientists tied this directly to rising baseline temperatures. A hotter atmosphere converts a slow drought into a fast one. It compresses the timeline. It removes the warning period. The drought spreading across America in 2026 had the fingerprints of this faster, crueler pattern all over it. And the force responsible for parking all that heat over the southeast had a name. It sat over the Atlantic Ocean, and it had been getting stronger. Picture a giant spinning lid over the Atlantic Ocean, roughly centered east of Bermuda. Air inside it spirals clockwise and sinks toward the surface. That sinking air is dry, dense, and hot. It pushes everything else out of the way. Rain-making weather systems, storm tracks, moisture flowing in from the Gulf of Mexico. All of it gets deflected north or south by this spinning wall. That system is called the Bermuda High, and in the spring of 2026, it shifted westward and intensified in a way that hasn't been seen in modern records. Under normal conditions, the Bermuda High sits well offshore and allows moisture from the Gulf and the Atlantic to roll across the southeast during spring and summer. Thunderstorm season fires up. Rain comes regularly. The soil stays reasonably wet. The system, while always present, behaves in a way the land and its ecosystems have adapted to over thousands of years. When it shifts west and strengthens, the whole equation changes. The storm tracks that normally deliver rain to Georgia, Florida, and the Carolinas get pushed north toward Virginia and New England, or blocked entirely. The southeast sits directly under the high-pressure dome. Skies stay clear, temperatures rise, and the land underneath starts drying out from above while the heat pulls moisture out of the soil from below. In 2026, this is exactly what happened. The Bermuda High parked itself over the region and refused to move. Week after week, the forecasts showed the same stubborn pattern. High pressure, clear skies, above normal temperatures. The moisture from the Atlantic and the Gulf stayed locked out. Some areas in the southeast recorded zero meaningful rainfall from late September of 2024 all the way through the following spring. That is roughly 7 months of almost nothing. Imagine filling a bathtub with a drain open and the faucet barely dripping. The water level only goes one direction. The soil was already pulling double duty, trying to sustain vegetation through a warmer and drier winter than usual before the spring heat even arrived. By March, the Palmer Drought Severity Index, the tool scientists use to measure long-term drought intensity across the country, hit its highest reading for the month of March since record-keeping began in 1895. That is a number that reaches back over 130 years. The Bermuda High also accelerated the flash drought problem. Because it brings extended heat alongside the lack of rain, it speeds up the rate at which soil loses moisture to the atmosphere. The combination of no input and fast output is a 1-2 punch that overwhelmed the southeast's water systems in a matter of weeks. The drought didn't just stop rain from falling, it changed the temperature profile of the entire region, baking the soil during months when it would normally be recovering from winter. What made scientists most uneasy was this. The Bermuda High behaves this way when ocean temperatures in certain parts of the Atlantic shift. And ocean temperatures in the Atlantic have been behaving strangely for years. The two systems are connected. One influences the other, which brought researchers back to a much larger question. Was the Bermuda High acting alone, or was it responding to something happening deeper in the ocean? Something below the surface, something that moves slowly, something that carries heat across an entire hemisphere. Florida is supposed to be wet. The state sits between the Gulf of Mexico and the Atlantic Ocean. In a normal year, afternoon thunderstorms roll in so reliably during summer that locals plan around them. By 3 in the afternoon, dark clouds build on the horizon, and within an hour, an inch of rain can fall in 30 minutes. It happens almost every day for months. That rhythm collapsed in 2026. The same Bermuda High that blocked rain from the rest of the southeast locked Florida in a dry vice. And Florida, with its flat terrain, sandy soil, and massive population, felt the effects faster and harder than almost any other state. By early spring, nearly all of Florida was under some level of drought. 80% of the state sat in extreme drought conditions. Cities and counties that had never considered restricting outdoor water use started posting signs. Lawn watering was limited to specific days of the week. Car washes were told to reduce operations. Homeowners started getting notices explaining why their water bills might change. For people who had lived in Florida for decades, this felt surreal. This was a state where the joke had always been that you didn't need to water your lawn because the sky would do it for you. The soil across Florida is mostly sand. Sand drains fast. In a wet year, that drainage is manageable because the rain comes back before the ground dries completely. But pull the rain away for weeks or months, and sandy soil gives up its moisture almost immediately. The water table drops fast, the plants feel it fast, and the fires start fast. Over 1,500 wildfires burned across Florida in the first 3 months of 2026 alone. That figure was already half the total number of fires recorded for the entire previous year, and summer hadn't arrived yet. The dried-out vegetation across the state had become a fuel load waiting for a spark, and the sparks were coming regularly. Communities in rural northern Florida were told to stay on alert. Smoke advisories went out across central and southern regions. The Everglades, the massive river of grass that covers the southern tip of the state and stores water for millions of people, started burning. Wetlands that are supposed to be too wet to catch fire were dry enough to burn. Water managers were facing a problem with no quick solution. Conservation orders could slow the rate at which people were drawing water from the system, but the rain that had been missing for months couldn't be replaced by a policy. The real damage was happening underground. Below Florida's surface sits one of the largest underground water systems in the world, a vast network of limestone rock filled with fresh water built up over thousands of years. Farmers and cities alike depend on it. And it was dropping. That underground system has a name, it has a history, and in 2026 it hit a level that hadn't been seen in 15 years. What that number meant for millions of Floridians, and for the farms that feed much of the eastern United States, was becoming very clear. And it wasn't good. Underneath Florida, Georgia, South Carolina, and parts of Alabama, there is a hidden ocean. It doesn't look like water. It looks like rock, porous limestone, riddled with cracks and caves and hollow spaces, all of it saturated with fresh water that has been filtering down through the ground for thousands of years. This system, called the Floridan Aquifer, stretches across roughly 100,000 square miles. It is one of the most productive underground water systems on the planet. Millions of people drink from it every day. Farms across the region depend on it for irrigation. Springs that feed rivers, lakes, and ecosystems get their water from it. In normal years, rainfall replenishes what is drawn out. The system stays roughly in balance. 2026 was not a normal year. With almost no rain falling for months, the recharge process stopped. Rain stopped filtering down through the soil. The limestone stopped refilling, but the demand never stopped. Farmers facing failed surface crops turned to the aquifer to keep their fields alive. Municipal water systems drew more heavily than usual as surface water supplies dried up. The aquifer absorbed all of it without getting any back. By spring, the Floridan aquifer had fallen to its lowest recorded levels since 2011. That was the last major drought to grip the region. 15 years of recovery, slowly built up through rain and careful management, had been erased in a single dry season. The consequences spread fast. Springs that usually flow with clear, cold water slowed to a trickle. Some stopped flowing entirely. The rivers they feed dropped. Ecosystems built around those rivers, the fish, the birds, the reptiles, the plant life, all came under stress simultaneously. In cities and towns across northern Florida, water managers started issuing conservation notices. Residents were asked to cut back on outdoor use. Some communities moved to mandatory restrictions. Water pressure in certain areas dropped enough that residents noticed it in their showers and faucets. For farmers, the pressure was even more immediate. Crops already stressed by the heat and lack of surface rain needed water from somewhere. The aquifer was the only option. But pulling heavily from an already depleted system is like spending the last money in your bank account during a crisis. It solves the immediate problem, but leaves nothing for what comes next. And what came next for the agricultural sector was already looking grim. The aquifer also plays a role in preventing something most Floridians don't think about. Along the coasts, salt water from the ocean sits just beyond the fresh water stored underground. As long as the aquifer stays full and pressurized, it holds the salt water back. When the aquifer drops, that barrier weakens. Salt water can begin pushing inland through the limestone, contaminating wells and water supplies in ways that take years to reverse. 15 years of recharge, gone in one season. The damage to the aquifer would not heal the moment rain returned. Scientists estimated that full recovery could take years of above-average rainfall, and even then, the structural shifts in the limestone itself from reduced pressure would take longer to fully understand. The ground was drying out from below and above at the same time. And above the ground, the landscape was doing something even more visible. It was burning. Before the drought even hit its peak, The stage for a catastrophic fire season was already being set. Earlier in 2026, a cold snap swept through the southeast. Temperatures dropped hard and fast across Florida, Georgia, and the Carolinas. Tropical plants that had never experienced frost got hit. Grasses that stay green through the mild southern winter turned brown. Shrubs and undergrowth that normally hold moisture died back quickly in the cold. Under normal spring conditions, new growth would come in and replace the dead material. Rain would keep everything damp, the dead vegetation would break down slowly. Fire risk would stay manageable. But then the drought arrived, and the rain that was supposed to spur new growth never came. The dead vegetation from the cold snap sat on the landscape, dried further by weeks of heat and no rain, and turned into something fire scientists call fuel load. Think of it like kindling spread across millions of acres. Every dead branch, every dry grass blade, every shriveled shrub, all of it waiting for a spark. In a normal year, fire managers plan for peak fire risk in May and June across the southeast. They pre-position equipment, run prescribed burns in winter to reduce fuel, and coordinate with weather forecasters to anticipate conditions. The system works because the timeline is predictable. In 2026, the fuel load was already critical by February and March. The timeline had shifted forward by 2 to 3 months. Equipment that should have been resting was already deployed. Staff that expected months of preparation were immediately responding to active fires. The system, built for a known pattern, was being asked to handle something outside its design. Fire behavior in heavy fuel conditions changes dramatically. Fires that might have burned slowly through sparse undergrowth in a wet year now moved fast and hot through dense bone-dry material. Spotting, where wind carries burning embers ahead of the main fire front and starts new fires hundreds of yards away, became much more common. Fire lines that a crew could normally hold became impossible to stop without air support. The smoke itself became a public health crisis. Air quality alerts went out across Florida for days at a time. Schools closed. Outdoor events were cancelled. Residents with asthma or other lung conditions were told to stay inside, and the fires kept coming. By late spring, the fire count in Florida alone was running at a pace double the historical average for the same period. Emergency resources were stretched thin. Counties were requesting mutual aid from neighboring states. The federal government moved aircraft and crews into the region weeks earlier than usual. The drought hadn't just dried out the land, it had transformed the southeast into one of the highest risk fire environments in the country, at a time of year when that risk is supposed to be low. And the fires that had already started were only a preview. One fire in particular, in a rural county in northern Florida, showed exactly how fast the situation could turn deadly. Numbers lose their meaning fast. 1,500 wildfires sounds like a statistic, something to put in a report, a data point in a briefing. But 1,500 separate fires, each one burning through someone's land, someone's trees, someone's neighborhood, is something different entirely. Start with the smoke. On the worst days in early 2026, you could smell it 50 miles from the nearest active fire. Driving through central Florida, the sky turned a dull orange by mid-afternoon. The sun looked pale and wrong, filtered through a haze of ash and particles. Locals posted photos online of skies that looked like a sci-fi movie. The color was real, the smoke was real. On the ground near an active fire, the noise is constant. Helicopters pulling water from nearby lakes and dumping it on the leading edge of the flames. Tanker planes making low passes, dropping red retardant across the treetops. Engines from every county in the region staged along dirt roads in the pines, trying to hold the fire at natural breaks before it jumped the line. The crews fighting these fires were working in brutal conditions, temperatures already above normal from the drought, no shade in burned areas, smoke so thick that visibility dropped to a few yards in the wrong wind. And the fire kept pushing, driven by fuel that had been drying for months and wind that came unpredictably. Fire managers use the word resource-strained carefully. It means the equipment and the people are already committed. and there is nothing left in reserve. By late February, Florida was resource-strained. By March, they were requesting help from out of state. By April, federal assets were deployed, and the state had declared multiple emergency orders. 1,500 fires in 3 months works out to roughly 17 fires every single day. Some were small, caught early, extinguished within hours. Others burned for days. A few burned for weeks before enough rain came from a passing storm system to knock them down. The land hit hardest was the pine flatwoods of northern and central Florida. This ecosystem is adapted to fire. Under natural conditions, lightning-sparked fires roll through every few years, burning the undergrowth, clearing dead material, and keeping the forest healthy. The problem in 2026 was intensity and timing. Fires that should have been routine became violent because the fuel load was too heavy and the moisture was too low. Fires that should have come in summer came in winter and spring, hitting ecosystems before they had any seasonal preparation. Wildlife was displaced on a massive scale. Animals that live in the flatwoods, gopher tortoises, fox squirrels, indigo snakes, sandhill cranes, had nowhere to go when the fires came faster than they could travel. Some moved toward roads and were hit by cars. Some moved toward neighborhoods and startled residents. Every fire that burned through the flatwoods also released carbon that had been stored in the soil and vegetation for years. Scientists call this a carbon pulse. The forest that burned becomes a source of greenhouse gases instead of a storage system, which feeds the cycle that made the drought worse in the first place. 1,500 fires, each one a piece of a larger story. One of them, in Calhoun County, made the news for reasons that hit closer to home than any statistic. Calhoun County sits in the Florida Panhandle. It is not a place most people outside Florida would recognize. Small towns, long stretches of pine forest, roads that run straight for miles through flat, open land. The kind of place where your neighbors are a quarter mile away and the nearest fire station might be 20 minutes down a county road. In March of 2026, a fire started in the dry brush somewhere in Calhoun County. The exact ignition point was under investigation, but the conditions were clear. The land was parched, the undergrowth was dead and dry from months without rain. The wind was blowing. Within hours, the fire had grown to over 500 acres. 500 acres is roughly the size of 500 football fields laid side by side. For a fire to reach that size in a single day, it needs fuel, heat, and wind. In Calhoun County that March, all three were present in abundance. The fire moved faster than crews could contain it. By the time equipment arrived and perimeter lines were being cut, the fire had already blown through its initial path and was reaching into areas where homes sat at the edge of the tree line. 16 homes were destroyed. That number, 16 homes, is the kind of statistic that looks small in a national report, but is enormous to the people who lived in those houses. The furniture, the photos, the records, the things people keep in a house for 20 years, for a lifetime, gone in a matter of hours. Evacuations were called fast, and because of that, no lives were lost. But the speed at which the fire consumed the structures shocked even experienced fire managers in the region. Houses that are near pine forest in wet conditions have some natural buffer. The trees hold moisture. The undergrowth is green. Fire that reaches a yard under those conditions burns slower, gives more warning. In drought conditions, that buffer disappears. Dry pine straw on the ground ignites like paper. Dry shrubs against a fence catch in seconds. A house that might have had 20 minutes of warning in a normal year had 5 in March of 2026. The families who lost homes in Calhoun County joined a growing list across the South and West. The insurance, questions, the temporary housing, the rebuilding process, all of it began while the rest of the county was still under evacuation advisory. The fire was eventually controlled. Rain from a brief frontal passage helped knock it down. but the land it burned through would take years to recover. The soil, scorched at high temperatures, loses its structure. Rain that eventually returns runs off instead of soaking in, increasing flood risk while doing almost nothing to recharge the aquifer below. One fire, 500 acres, 16 homes, one county. Multiply that story across the 1,500 fires burning through Florida that spring, and across the dozens of counties touched by the drought, and the scale of what was happening begins to take shape. But the fires were only the most visible damage. Underground, a slower crisis was playing out. And in the fields, the financial toll was already past the point where most farmers could absorb it alone. A farm doesn't fail all at once. It fails in layers. First the yield drops, then the quality drops, then the water runs short, then the feed for the animals runs out, then the math stops working, and a family that has been farming the same land for 3 generations starts doing calculations they never thought they would have to do. By spring of 2026, farms across the southeast were deep into that process. The drought had moved through every layer of agricultural damage faster than anyone had planned for. The total agricultural losses across the region crossed $3 billion. $3 billion is a number that sounds like it belongs in a government budget, not a conversation about tomatoes and cattle. But that figure represents individual losses stacked on top of each other across thousands of farms. A vegetable grower in Florida who lost 60% of his spring crop, a cattle rancher in Georgia who spent twice his normal budget on hay because the pastures were dead, a citrus operation in the central part of the state that had already been struggling after a decade of disease and cold damage, now facing a drought on top of everything else. Florida is one of the most important agricultural states in the country. During the winter and spring months when most of the country is too cold to grow fresh produce, Florida supplies a significant portion of the tomatoes, peppers, cucumbers, strawberries, and citrus that end up on grocery store shelves from Maine to Minnesota. When Florida farms fail, the supply tightens, prices climb. Grocery shoppers in the Midwest who had never heard of the Calhoun County fire or the Floridan aquifer started noticing the drought anyway. Strawberry prices jumped in March. Tomato prices followed in April. Orange juice, already expensive from years of citrus disease, climbed further. The cattle sector took a different kind of hit. Beef cattle in the southeast rely heavily on pasture grass. Pasture grass needs rain. With rain absent for months, ranchers had 2 choices: pay inflated prices for hay trucked in from elsewhere, or sell animals early at reduced prices to cut feed costs. Both options meant financial losses. Many chose both. Farmers who had crop insurance found the claims process slow and in many cases insufficient to cover the actual damage. Insurance payouts are based on historical averages, and the 2026 losses in many categories exceeded anything the historical models had been built to cover. Government disaster declarations opened some emergency relief funds, but the timeline for those funds to reach individual farmers typically runs months behind the crisis that triggered them. Farmers who needed help in March were still waiting in June. The economic damage wasn't limited to farms. Packing houses that process produce had less product to handle, which meant fewer hours for workers. Trucking companies that move agricultural products had fewer loads. Small towns built around farming economies saw less money circulating through their stores and businesses. $3 billion, and the summer, historically the harder season for drought, hadn't even arrived yet. Below the fields, something else was running out even faster than the money. When the rain stops, farmers go underground. It sounds simple: if the sky won't give you water, pull it out of the earth. That is exactly what thousands of farms across Florida, Georgia, and the Carolinas did in the spring of 2026. Wells were drilled deeper. Pumps ran longer hours. Irrigation systems that normally supplemented rainfall became the only source of water keeping crops alive. The Floridan aquifer, already stressed by the lack of rain recharge, absorbed this demand on top of everything else. cities drawing more water for their residents, rural homeowners pumping more for their households, farms pulling heavily to keep fields alive, all of it coming out, nothing going back in. The aquifer is not an underground lake, the image most people carry in their heads, a giant pool of water sitting beneath the surface, is wrong. The aquifer is more like a massive sponge made of limestone. Every hole, every crack, every hollow space in the rock holds water. When you pump it out faster than rain refills it, the sponge starts to dry. And a limestone sponge that dries doesn't just bounce back when rain returns. As the water level drops inside the aquifer, the pressure inside the rock drops with it. Along Florida's coasts, this pressure is what keeps salt water from the ocean from moving inland through the limestone. Fresh water pushes out toward the coast. Salt water stays offshore. That balance depends on the aquifer staying full. Drop the aquifer level significantly, and the balance shifts. Salt water begins migrating inland through the same porous limestone that holds the fresh water. It contaminates wells. It makes groundwater undrinkable. It damages the roots of crops that can't tolerate salt. And once salt water gets into a well or a section of aquifer, removing it takes years and enormous amounts of energy. Several communities in coastal counties were already beginning to test their wells more frequently by spring of 2026. Some coastal wells showed rising salinity readings, meaning the salt water was already on the move. Farmers knew what they were risking. Pulling heavily from the aquifer during a drought is understood to be a short-term solution with long-term costs. But the alternative, watching an entire season's crop die in the field, was financially ruinous immediately. Many chose the damage they could deal with later over the loss they couldn't survive now. Some farmers hit the physical limits of their wells before the crop season ended. The pump drew air. The water was gone from that depth. Drilling deeper was expensive and slow. Some fields went unwatered in the final weeks of the growing season, and the crops in those fields were abandoned. The groundwater crisis wasn't just a Florida story. Across the southeast and into parts of the southwest and high plains, aquifers were being drawn down faster than science had projected. The 2026 drought accelerated a trend that water scientists had been watching with concern for years. And underground water, unlike surface water, doesn't recover quickly when rain returns. A lake can refill in a season. An aquifer can take decades. But there was one body of water in Florida that had become a symbol of just how severe the surface water situation had gotten. A lake in the middle of the state that supplies fresh water and controls flood patterns for millions of acres of farmland, it was hitting its lowest level in 15 years. And what that meant for southern Florida was complicated and urgent. Lake Okeechobee is the liquid heart of southern Florida. It sits in the middle of the state, like an inland sea. At full capacity, it covers roughly 700 square miles, making it the largest lake entirely within the continental United States. Water managers use it as a reservoir, releasing water south into the Everglades during dry periods and drawing it down before hurricane season to create storage capacity for storm surge. Farmers around its rim depend on it for irrigation. Cities downstream depend on it for drinking water supply. The ecology of southern Florida is built around its water levels. In the spring of 2026, Lake Okeechobee fell to its lowest level in 15 years. The visual impact was striking. Wide mudflats appeared at the lake's edge, where water had stood just months before. Boat ramps extended into air. Vegetation that normally stays submerged stood dry and dead in the exposed muck. The ring of brown mud around the lake's perimeter grew wider week by week. The practical consequences moved fast. Water releases to agricultural operations south and west of the lake were reduced. Farmers who had been counting on scheduled releases to supplement their own pumping suddenly had less coming to them. The reduction came at the worst possible time, right in the middle of planting season. For water managers, the situation required a set of competing and nearly impossible trade-offs. Release too much from the lake to help agriculture, and you run the risk of the lake dropping below the threshold where it can support its own ecology. Keep the lake too low for too long, and the exposed muck at the lake bed can catch fire. Yes, lake mud can burn when it gets dry enough. The organic material in the lake bed sediment is combustible. It has happened before at Okeechobee during past droughts, and smoke from a burning lake bed is a different kind of surreal. The cities that draw water from the lake's watershed began looking at their reserve supplies and running calculations about how long those reserves would last if the lake kept dropping. Several municipalities issued voluntary conservation requests. Tourism and recreation around the lake, a significant local industry, took a hit. Fishing guides who work the lake year-round found their boats grounding out in areas that had been navigable for decades. Charter bookings dropped as word spread about the low water conditions. The ecosystem inside the lake was under pressure too. Fish that spawn in shallow areas near the shore found those areas either exposed or so shallow that water temperatures became lethally high. Wading birds that feed along the lake's edges had to travel further to find productive foraging areas. Lake Okeechobee is the system that the rest of southern Florida's water network is built around. When it drops, every downstream system feels it in sequence. The farms, the cities, the Everglades. And the Everglades, that massive wetland wilderness that covers the southern tip of the state, was facing something that the people who built it, and the scientists who study it, had never quite expected to see. It was burning. The Everglades is supposed to be impossible to burn. It is a slow-moving river of fresh water, 50 miles wide and 100 miles long, spreading from Lake Okeechobee south to the Florida Bay. The water moves so slowly it looks still, just a few inches deep in most places, flowing imperceptibly through sawgrass and mangrove. Every spring, the water levels drop slightly as the dry season arrives. Every summer, the rains return, and the whole system floods back up. That seasonal rhythm is the heartbeat of the Everglades. The plants, the animals, the fish and birds and reptiles, all of them evolved around that pulse of wet and dry. The system can handle the dry season because it knows the wet season is coming. In 2026, the dry season arrived. The wet season didn't. Water levels in the Everglades dropped below what the system had seen in decades. The sawgrass, which under normal conditions stands in water up to its ankles all year round, found itself standing in dry ground. The peat soil beneath the grass, built up over thousands of years of slow decomposition, dried out, and dried peat burns. Fires started in sections of the Everglades that hadn't burned in living memory. The sawgrass caught first, burning hot and fast across the open expanses. Then the peat beneath began to smolder. Peat fires are different from surface fires. They don't just burn the top of the ground, they burn into the ground itself, consuming the soil layer by layer, sometimes reaching several feet deep. Peat fires can smolder for weeks or months, invisible underground, even surviving rainfall that would extinguish a surface fire. When peat burns in the Everglades, it doesn't just release carbon into the atmosphere. It destroys the physical foundation of the ecosystem. The soil that took thousands of years to build disappears. The elevation of the land drops. Areas that were once high enough to stay above water during the wet season sink lower, changing the hydrology of the entire region. The land itself is smaller when the fire is done. For the communities south of the Everglades, including the suburbs and cities of Miami-Dade and Broward counties, the smoke was the most immediate problem. Air quality alerts covered one of the most densely populated parts of Florida for days at a time. Hospitals reported increases in respiratory visits. Schools closed. The deeper concern was what the fires meant for the water supply. The Everglades acts as a natural filter and storage system for the fresh water that flows south from Lake Okeechobee. That filtered water eventually recharges the shallow aquifer that supplies Miami and surrounding cities with their drinking water. A damaged Everglades is a damaged water supply for millions of people. Ecologists who had spent careers studying the Everglades described what they were seeing in 2026 as a stress event without precedent in the modern record. The wetland designed by nature to be fireproof was burning, and the question scientists were now asking wasn't just why, it was whether this was a one-time extreme event or whether the climate had shifted far enough that the Everglades would now face this threat every few years. That question pointed back to the ocean and to something happening in the Atlantic that had been building for a very long time. Most catastrophes arrive with noise. Earthquakes crack roads and bring down buildings in seconds. Hurricanes announce themselves days in advance, with spinning satellite images and urgent evacuation orders. They are impossible to miss. A drought arrives in silence. There is no single day you can point to and say, that is when it started. No alarm goes off. No news alert breaks through. The grass just stays a little drier than usual. The stream runs a little lower. The afternoon storm that was supposed to arrive by 3 o'clock doesn't come. And then it doesn't come again and again. Some parts of the southeast went without meaningful rainfall from late September of 2024 through the following spring. That is roughly 7 months. 2 full seasons, the span of an entire school year. Think about what 7 months without rain actually means at ground level. In September, the soil is at its driest from summer. Normally, fall brings cooling temperatures and the first meaningful rains in months. The ground begins to recover, streams stabilize, farmers plant fall crops knowing winter moisture is coming. In 2024 and into 2025, that recovery didn't happen. October came and went with almost no rain. Over 70 weather stations across the country recorded their driest October ever. The soil, already dry from summer, never got the reset it needed going into winter. Winter arrived lighter than usual. Mountain snowpack in the Appalachians, which feeds rivers across the east as it melts in spring, came in below average. The rivers that depend on that snowmelt were already running lean by January. Then spring arrived, the season when farmers need moisture the most, the season when the country's agricultural machine kicks into its most intense period of planting and early growth. And the rain still didn't come. By March, the Palmer Drought Severity Index reached its highest reading for that month since 1895. That record stretches back through the Dust Bowl years, through the Great Depression, through every dry spring in American history. March of 2026 was the worst in over 130 years of records. The compounding effect is what made this drought so destructive. Each month without rain made the next month's deficit worse. Soil that spent October dry went into November without recharge. Soil that spent November dry went into December at a deeper deficit. By the time spring arrived, the ground wasn't just dry from recent weeks, it was dry from months of accumulated loss. Water managers who track soil moisture levels watched the numbers drop week after week and ran projections forward. The models were grim. Even if spring rains arrived on time and in normal amounts, which they didn't, the soil deficit was deep enough that full recovery would take the entire summer and possibly into fall. The rains didn't arrive on time. They didn't arrive in normal amounts. The deficit kept growing, 7 months of silence from the sky. And below the dry fields, below the cracked soil and the exhausted aquifer, something even larger was changing. Something that had been quietly shifting for years before anyone in Florida noticed the grass starting to brown. It was happening in the ocean, and it was happening at a scale that made the drought look like a local problem. Scientists need a way to measure how bad a drought really is. Rainfall totals alone don't tell the full story. An area that usually gets 20 inches of rain in the spring and gets 15 instead is experiencing a drought. An area that usually gets 5 inches and gets 4 is also experiencing a drought. The same 10-inch shortfall means something very different depending on what the land and its systems are adapted to. The Palmer Drought Severity Index solves this problem. It measures drought relative to what is normal for a given region, factoring in temperature, evaporation, and soil moisture, alongside rainfall. A score of -2 signals moderate drought. -3 is severe. -4 is extreme. In March of 2026, the National Palmer Index hit levels that hadn't been recorded for that month since 1895. That means, looking back through the Dust Bowl of the 1930s, through the severe droughts of the 1950s and 1980s, through every dry spring in over a century of record-keeping, and finding that March 2026 was worse than all of them for that time of year. The 1895 reference point matters because it is the beginning of reliable, widespread weather records in the United States. Scientists can't say with certainty that no March before 1895 was this dry, but they can say that for every spring in the entire modern era, this one was the worst. What the index captures that raw rainfall numbers miss is the compounding effect of heat. A warm drought evaporates soil moisture faster than a cool one. In 2026, the Southeast was experiencing both. Rainfall was far below average, and temperatures were running well above normal simultaneously. The Palmer Index captured both pressures together and reflected a combined soil moisture deficit that was historic in scale. For anyone trying to communicate the severity of the situation, the index provided a single number that cut through the complexity. Water managers used it to justify emergency declarations. Farm assistance programs referenced it when calculating aid amounts. Insurers used it to assess claims. But for the people living through it, the number was almost irrelevant. What mattered was the cracked ground outside the window, the dry creek bed where the cattle used to drink, the field that should have been green and wasn't. The index also revealed something important about geography. The readings weren't uniform across the country. The Southeast registered the most extreme values, but drought of varying severity covered enormous portions of the South, the Southwest, and parts of the Mountain West. The country wasn't just experiencing a regional dry spell, it was experiencing a broad connected pattern of dryness that traced back to atmospheric and oceanic conditions operating at continental scale. Somewhere in the data, climate scientists were seeing the fingerprints of a system much larger than any single weather pattern. A system that moved heat and moisture across entire ocean basins. A system that, according to new research, published just weeks earlier, was slowing down faster than anyone had projected. And when that system slows down enough, rainfall patterns across an entire hemisphere begin to shift in ways that a drought index, no matter how sophisticated, was never designed to capture. There is a number that water scientists use to describe how deep a drought deficit goes. Recovery rainfall, the amount of precipitation a region would need, falling all at once or over a very short period, to bring soil moisture and reservoir levels back to baseline. For most droughts, this number is uncomfortable but imaginable, a few extra inches over a few months. A wet winter following a dry fall. For eastern Texas in the spring of 2026, the recovery rainfall estimate was 19 inches in a single month. 19 inches is more than Houston typically receives in its 4 wettest months combined. It is roughly the entire annual rainfall for El Paso. For eastern Texas to receive 19 inches in 30 days, it would need a series of tropical systems or a stationary frontal pattern delivering rain week after week without stopping. That kind of rainfall in that concentration over that shorter period is so rare that climate scientists essentially classify it as outside the range of normal variability, which means the deficit in eastern Texas and in portions of the surrounding region was deep enough that natural weather patterns alone were unlikely to close it in any reasonable time frame. The practical implication of a deficit that large is that the landscape doesn't just stay dry, it begins to change. Soil compacts as moisture leaves it. Clay soils shrink and crack, creating channels that cause future rain to run off rather than soak in. Native grasses and deep-rooted vegetation die back, and the plants that replace them when moisture eventually returns are often less drought-resistant and less able to hold soil in place. Rivers and creeks that had already dropped to low levels began losing their base flow entirely in some areas. Base flow is the water that keeps a river running even during dry periods. It comes from groundwater seeping slowly into the riverbed. When aquifers drop far enough, that seepage stops. Rivers stop flowing. They become a series of disconnected pools, then dry beds. For Texas, which had been managing water scarcity issues for years before 2026, the drought added a new layer of stress onto systems already under pressure. Reservoirs that supply cities like Dallas and San Antonio had been drawn down. The replenishment that normally comes from winter rains and spring storms had been minimal. Farmers in eastern Texas who grow rice, cotton, and grain sorghum depend on surface water deliveries from river systems and reservoirs. With those systems low, water allocations were cut. Some farmers received less than half their normal allotment. Some received nothing. The planting decisions that followed, what to grow, whether to plant at all, how deep to draw from private wells, were some of the hardest farmers in the region had faced in a generation. The 19-inch figure travelled fast once it appeared in public briefings. It became a shorthand for the scale of the problem. People understood intuitively that 19 inches in 1 month was impossible, which meant understanding for the first time that parts of the country might be stuck in this drought for years. That realization landed differently in a region already watching its water tables drop, its rivers slow, and its farmers sell cattle early just to keep the bills paid. And the drought wasn't staying put. It was spreading west and linking up with a completely separate water crisis building in the mountains. The drought that started in the southeast didn't stay there. By spring of 2026, dry conditions had spread west across the Gulf states, through Texas, and into the mountain west, where they merged with a different but connected water crisis. The mountains that feed the Colorado River, the Rio Grande, and the rivers of the Pacific Northwest had come through winter with far below average snowpack. The rivers fed by that snowpack were already running low before the spring drought even peaked. Snowpack is the mountain's version of a reservoir. Over winter, snow builds up in the high country, sometimes accumulating dozens of feet deep in the passes and peaks. When spring arrives, that snow melts slowly, releasing fresh water into rivers over a period of months. It is the reason that rivers in the west can keep flowing through the hot, dry summer months. The mountains are storing winter rain and releasing it gradually. In the winter of 2025 into 2026, the snowpack across large portions of the Rockies and the Sierra Nevada came in at 60 to 70% of normal in the hardest hit areas. Some high elevation stations recorded their lowest snowpack readings in decades. When the spring melt arrived, it delivered a smaller and shorter pulse of water than the rivers downstream depended on. The Colorado River, already under extreme pressure from decades of overuse and 2 decades of lower than average flow, received one of its weakest spring pulses in the modern record. Lake Mead and Lake Powell, the 2 massive reservoirs that store Colorado River water for tens of millions of people across the Southwest, both finished the spring at levels that triggered water shortage declarations. The Rio Grande, which provides water for farms and cities from Colorado through New Mexico and Texas and into Mexico, slowed to a trickle in several stretches by late spring. In some years, the Rio Grande runs dry in parts of its lower stretch for brief periods. In 2026, it ran dry earlier, in more places, and for longer. For the farmers who depend on these rivers, the math was brutal. Surface water deliveries were cut. Groundwater pumping intensified, the same pattern playing out in Florida, where surface shortfalls drove heavier groundwater use, was repeating itself across thousands of miles of American farmland simultaneously. The drought in the southeast and the snowpack deficit in the west weren't the same weather event. They had different immediate causes, but they shared a common background condition, a warming climate that was making dry years drier, reducing the buffer that water systems had historically counted on between one bad year and the next. Scientists tracking both events noted that the simultaneous occurrence of drought in the east and snowpack failure in the West was exactly the kind of compound stress event that water infrastructure in the United States had not been built to handle. Systems designed for one crisis at a time were managing two at once. And underneath both crises, a third process was at work. Slower, larger, operating not on the scale of months or seasons, but on the scale of decades. It moved through the Atlantic Ocean. It had been running for thousands of years, and something was slowing it down. Imagine a conveyor belt running through the entire Atlantic Ocean. Warm water near the surface moves north from the tropics, carrying heat up toward Europe and the northeastern United States. As it travels north, it cools. Cold water is denser than warm water. When this warm current reaches the North Atlantic, it cools enough to sink toward the ocean floor. Once it sinks, it flows south along the bottom of the ocean, underneath the surface current moving north above it. This loop, warm water moving north on the surface, cold water moving south along the bottom, circles through the entire Atlantic basin. It carries enormous amounts of heat. Its influence on climate reaches into Europe, North America, Africa, and South America. It has been running in roughly its current form for thousands of years. Scientists call it the Atlantic Meridional Overturning Circulation. The scale of this system is almost impossible to picture. The volume of water it moves is more than 100 times the flow of the Amazon River. The heat it transports northward is comparable to the output of more than 1 million power plants running continuously. It is one of the most powerful climate-regulating systems on the planet, and its behavior is not optional for the climate that billions of people depend on. Western Europe sits at a latitude similar to Canada. London is at roughly the same latitude as parts of Labrador. Oslo is higher than the southern tip of Greenland. By geography alone, Europe should be far colder than it is. The reason it isn't is largely this ocean current. The warm water moving north releases heat into the atmosphere above it. That heat drifts east across the Atlantic and warms the air over Europe, keeping winters there mild compared to the same latitudes in North America. The current also affects rainfall. As it moves warm, moist air northward, it influences where storm tracks form, where precipitation falls, and how moisture is distributed across large portions of the northern hemisphere. The rains that fall on West Africa, the storm tracks that bring moisture to the American southeast, the snowpack that builds in the mountains of Scandinavia. All of these are shaped in part by this ocean current. It is not a simple on-off switch. It has been varying in strength for thousands of years, following cycles tied to ice ages and interglacial periods. During the last ice age, when enormous amounts of fresh water flooded into the North Atlantic from melting glaciers, the current slowed dramatically. The climate consequences were severe and widespread, affecting temperature and rainfall patterns across the northern hemisphere for centuries. That history is not just a scientific curiosity, it is a warning, because the same thing that slowed the current thousands of years ago is happening again right now. Fresh water from melting polar ice is flowing into the North Atlantic, and according to a study published in April of 2026, the current is weakening at a rate that previous climate models had significantly underestimated. The number attached to that finding was alarming, and it changed the way scientists were thinking about the drought spreading across the United States. The Atlantic Meridional Overturning Circulation runs on two things: heat and salt. Warm, salty water moves north along the surface. As it travels, it releases heat into the atmosphere above it. By the time it reaches the North Atlantic, it has cooled significantly. Cold water is denser than warm water, but the salt content of this water makes it even denser. That combination of cold and salty causes the water to sink rapidly toward the ocean floor, driving the entire circulation forward. Remove the salt, and the engine loses its power. That is exactly what is happening. Glaciers in Greenland are melting at a rate that has accelerated sharply over the past 2 decades. The Greenland ice sheet holds enough frozen water that if it melted entirely, global sea levels would rise by over 20 feet. It is nowhere near fully melting. But the edges, the glaciers that flow from the ice sheet into the ocean, are carving and melting at a pace that was considered unlikely in climate projections from just 15 years ago. When glacial ice melts into the ocean, it releases fresh water. Fresh water does not carry the same salt content as ocean water. When enormous volumes of fresh water pour into the North Atlantic, they dilute the surface layer of the ocean, reducing its salinity. Less salty water is less dense. Less dense water does not sink as readily, and when the water stops sinking in the North Atlantic, the conveyor belt loses the engine that drives it. Think of it like a drain in a bathtub. The circulation in the North Atlantic is the drain. The warm surface current flowing north is the water rushing toward it. If you fill the tub with something that doesn't drain as easily, the whole flow slows down. The Arctic is also melting. Sea ice that used to cover large portions of the Arctic Ocean year-round has been retreating for decades. The summer minimum sea ice extent has been shrinking. This matters for the circulation because sea ice formation also drives salinity changes. When ocean water freezes, the salt stays behind in the surrounding water, making it saltier and denser. Less sea ice formation means less of this salt concentrating process, which further reduces the density of water in the North Atlantic. The two processes, glacial melt from Greenland and reduced sea ice formation in the Arctic, are happening simultaneously and reinforcing each other. Both push in the same direction. Both reduce the density of North Atlantic surface water. Both weaken the sinking that drives the current. Scientists have been tracking the salinity and temperature profiles of the North Atlantic for decades. The data shows a clear freshening trend in the surface layers, meaning the water is becoming less salty over time. The fingerprints of this freshening match the pattern expected from increased glacial and ice melt. The circulation has not stopped, it is still running, but the measurements show it is running more slowly than it was 50 years ago, and the rate of slowdown has been increasing. A team of researchers analyzing data from ocean sensors, satellite measurements, and deep water sampling published findings in April of 2026 that put a specific and troubling number on just how fast the slowdown had become. That number was 60% faster than the models had predicted. And what that means for the weather patterns billions of people depend on is something the research community is still working to fully understand. But the early picture is not reassuring. In April of 2026, a research team published findings that landed hard in the climate science community. They had spent years analyzing ocean data, temperature readings from sensors dropped deep into the Atlantic, salinity measurements taken across decades of ocean surveys, satellite observations of sea surface temperature, reconstructions of current strength built from sediment cores pulled from the ocean floor, which carry chemical signals of past ocean conditions going back thousands of years. The conclusion was stark. The Atlantic meridional overturning circulation was weakening at a rate approximately 60% faster than the average of all previous climate models had projected for this period. 60% faster sounds like a technical number. To understand what it means, think of it this way. The models that governments, cities, and infrastructure planners used to prepare for climate change were built on projected timelines. Those timelines assumed the current would weaken at a certain pace. Policies were set. Adaptation plans were written. Engineers designed coastal infrastructure to handle sea level rise by a certain decade. Agricultural planners projected rainfall changes on a certain schedule. The new data said all of those timelines were too slow. The change was happening faster than the plans assumed. The researchers were careful with their language, as scientists are. They noted uncertainties. They flagged the limitations of their data. They acknowledged that projecting the exact future behavior of a system as complex as the Atlantic circulation carries significant error ranges. But the direction of the finding, that the weakening is accelerating beyond what models anticipated, was described as robust across multiple independent data sources. The 60% figure came from comparing the rate of observed weakening against the distribution of projections from the major climate models used by international scientific bodies. The observed rate sat well outside the range that most models had considered likely for this point in time. A few models, the more aggressive ones, had projected faster weakening. The real-world data was tracking closer to those outliers. For climate scientists, an observation tracking with the more extreme end of model projections is a warning signal. The models that underestimated past change tend to also underestimate future change. The study landed in April of 2026, while the southeast was already burning and drying in the worst spring drought on record. The timing was striking. Researchers were careful to note that attributing a single seasonal drought directly to the circulation slowdown is scientifically difficult. Weather is complex. The Bermuda High that blocked rain from the southeast has natural variability built into it, but the broader pattern of shifting storm tracks, changing rainfall distributions, and a weakening climate engine in the Atlantic aligned with the direction that a slowing circulation would push things. The study didn't answer every question, it opened new ones. How much faster would the weakening continue? What specific threshold would trigger larger changes in weather patterns? Was the current still recoverable, or had the freshwater influx from melting ice already committed it to a certain trajectory? Those questions were still being debated, but one thing the study made clear was that the timeline was shorter than the world had been planning for, and the consequences of a significantly weaker current were already understood well enough to be alarming. Rain doesn't fall randomly. It falls where the atmosphere is warm enough to carry moisture, where wind patterns converge, and where conditions force that moisture to rise and cool and condense. Change the underlying ocean temperatures and atmospheric patterns that set up those conditions, and you change where the rain falls. The Atlantic meridional overturning circulation is one of the most powerful organizers of rainfall patterns across the Western Hemisphere. When it weakens, that organization breaks down in ways that are not subtle. The most direct effect on the Americas is a southward shift of the intertropical convergence zone. This is the band of heavy rainfall that circles the globe near the equator, driven by where warm ocean surfaces cause air to rise. The Atlantic current plays a role in keeping this rain band positioned where it is. As the current weakens, the North Atlantic cools relative to the South Atlantic. The rain band responds by drifting south. For the Amazon rainforest, which depends on predictable monsoon rainfall driven in part by Atlantic conditions, a southward shift of this rain band means drier conditions in the northern Amazon and potentially wetter conditions further south. The northern Amazon is already experiencing intensifying droughts. Scientists studying the region have warned that portions of it may be approaching a tipping point where the forest can no longer generate enough of its own rainfall through evaporation to sustain itself. For Central America and the Caribbean, the rainfall changes are less predictable but expected to be significant. These regions already experience high variability in rainfall tied to Atlantic sea surface temperatures. A weaker current carrying less heat north changes those temperature patterns and the rainfall that depends on them. For the United States, the connection runs through the storm tracks and moisture delivery systems that the current influences. The warm water moving north along the American East Coast acts as a moisture source and a steering mechanism for weather systems. As the current weakens and that warm water moves differently, the storms that track inland and deliver rainfall to the southeast follow different paths. Some research suggests that a weaker current shifts storm tracks northward, meaning more rain for the northeast and less for the southeast, which is exactly the pattern the southeast was experiencing in 2026. The drought gripping Florida, Georgia, and the Carolinas was consistent with the rainfall redistribution expected from a weakening circulation. Scientists stop short of saying the current caused the drought directly. The attribution is complex, but the patterns lined up. For South America, a weaker current has been linked to changes in the monsoon that Brazil and neighboring countries depend on for agriculture. Changes to that monsoon could affect crop production across a continent that feeds a significant portion of the world. The rainfall consequences of a weakening current weren't a single dramatic event. They were a slow redistribution, areas that used to be wet getting drier, areas that used to be dry getting wetter or more chaotic. Agricultural systems built over centuries on the assumption that the rain would keep coming to a certain place at a certain time of year, finding that assumption no longer holds. For Europe, the consequences of a slowing current played out differently, and in some ways more immediately dramatic. It seems backwards at first. The planet is warming, temperatures are rising across most of the globe, and yet, as the Atlantic meridional overturning circulation weakens, parts of Europe face the prospect of getting significantly colder. Not warmer, colder, winters that become longer and more severe, growing seasons that shorten, energy demand that spikes. The reason comes back to what the current does for Europe. It carries enormous volumes of warm water north from the tropics and releases that heat into the atmosphere above the North Atlantic. That heat drifts east on prevailing winds and keeps Europe dramatically warmer than its latitude should allow. England, France, Germany, Scandinavia, all of them sit at latitudes where, without the current's heat contribution, their climates would resemble those of Alaska or northern Canada. When the current weakens, less warm water makes it north. The North Atlantic cools. The heat that normally drifts east toward Europe diminishes. Temperatures in parts of northwestern and northern Europe begin to drop, even as the rest of the planet warms. This creates an unusual situation where a region experiences cooling within a globally warming climate. The cooling effect from the weakened current competes with the warming effect from greenhouse gases. Depending on how fast the current weakens relative to how fast overall warming continues, Europe could experience cooling winters even while summer heat waves intensify. The seasonal contrast sharpens. The agricultural implications for Europe are significant. Wine-growing regions in France and Germany have already shifted their harvest timing by weeks over the past century as temperatures climbed. A reversal of that warming, even partial, disrupts planting calendars, changes which crops are viable at which latitudes, and forces adaptation in agricultural systems that have spent decades adjusting in the other direction. Energy systems would also face pressure. Heating demand in northern Europe would rise. Countries that have been transitioning away from fossil fuels toward renewable energy built forecasts for those transitions on climate models that assumed continued warming. A period of cooling, driven by the weakened current, would strain those forecasts. The cold wouldn't arrive evenly. Scientists project the greatest cooling in the waters south of Greenland and Iceland, areas where the sinking that drives the circulation normally occurs. Sea surface temperatures in those areas have already been running anomalously cold compared to surrounding ocean regions, a pattern that researchers describe as a fingerprint of the slowing current. The people in Scotland, Ireland, and Scandinavia who would feel this cooling most directly are not causing it. The emissions driving glacial melt and the current slowdown come primarily from large industrial economies. The consequences fall unevenly across the globe, with some of the coldest winters arriving in countries that contributed least to the problem. The cooling in Europe is one piece of the current's influence. Further south, along the coasts of West Africa, the slowing current reduces the upwelling of cold, nutrient-rich water that fishing communities have depended on for generations. Fisheries decline, food security shifts, and along the east coast of the United States, the weakening current was doing something else entirely, something that the cities built along that coastline were already beginning to feel beneath their feet. The sea was rising, and it was rising faster there than almost anywhere else on Earth. The east coast of the United States is sinking into the sea faster than the global average. Sea level rise is a global phenomenon driven by melting ice and warming oceans, but the rate of rise is not the same everywhere. Along the coast from North Carolina up through Virginia, Maryland, New Jersey, and New York, the water is rising at 2 to 3 times the global average rate. Scientists call this region a sea level rise hotspot, and the Atlantic meridional overturning circulation is one of the reasons. Here is the mechanism. The current moving warm water northward along the east coast acts like a spinning top. It creates a slight gradient in sea surface height, pulling water away from the coast and keeping it elevated in the middle of the Atlantic. As long as the current runs strong, this effect helps keep sea levels along the east coast slightly lower than they would be otherwise. When the current weakens, that effect diminishes. The water that was being pulled away from the coast relaxes back toward it. Sea levels along the east coast rise faster than the global average. The slowdown of the current adds inches to what melting ice and warming water are already contributing. For coastal cities, inches matter enormously. Washington, a city built largely on low-lying land near the Potomac River, has seen its tidal flooding frequency increase dramatically over the past few decades. Streets in the historic district of Annapolis, Maryland, flood during high tides without any storm involved. Parts of Miami Beach flood regularly from groundwater, pushed up through porous limestone by a rising water table driven by the rising sea. These cities have been building infrastructure responses, flood barriers, pump systems, raised road surfaces, elevated electrical equipment. The costs run into hundreds of millions of dollars per city. The projections driving those investments assume a certain rate of sea level rise over certain decades. If the current weakens faster than those projections assumed, the flooding arrives ahead of schedule. Infrastructure built to last until 2050 floods in 2040. Plans that assumed decades of preparation time compress. The financial burden on coastal cities, already enormous, expands. The economic assets sitting in the sea level rise hotspot along the East Coast are extraordinary. Washington, Philadelphia, Baltimore, New York, Boston, the financial districts, the ports, the airports, the hospitals, the power plants, the water treatment facilities, all of it concentrated in a strip of coast where the ocean is rising faster than the rest of the world. The connection between the ocean current and the rising sea along the East Coast is one that most people living in those cities have never heard of. They are aware of sea level rise. They may have seen the flooding maps. But the role of a slowing Atlantic current in accelerating their specific local risk is a connection that has only recently entered scientific literature, with sufficient clarity to inform policy. The researchers who published the April 2026 findings on the current's accelerating weakening flagged this coastal implication directly. The East Coast hotspot was not going to wait for the current to collapse entirely. The slowdown already underway was already contributing to the faster rise already being measured. And the debate among scientists about what came next was growing more urgent. There are two schools of thought among climate scientists about what happens next to the Atlantic meridional overturning circulation. The first says the current will weaken gradually over decades. The slowdown will be significant. The effects on climate will be serious, but the change will be spread out over enough time that societies and ecosystems can adapt, imperfectly but meaningfully. The second says the current could reach a tipping point, a threshold beyond which the weakening accelerates suddenly and dramatically, shifting the circulation into a new and much weaker state within years or decades rather than centuries. This scenario is sometimes called a collapse, though scientists prefer more precise language. The debate is real and the stakes of getting it wrong are enormous. The gradual weakening camp points to the complexity of the ocean system. The Atlantic circulation interacts with dozens of other climate processes. It has a certain inertia. Large ocean systems don't typically change overnight. The models that project gradual weakening have been refined over decades and incorporate enormous amounts of observational data. The consensus view among most major climate bodies remains that dramatic collapse this century is possible, but not the most likely outcome under current projections. The tipping point camp points to past behavior. The last ice age saw the Atlantic circulation change dramatically multiple times, in relatively short periods, geologically speaking. Sediment cores from the ocean floor show these events as abrupt shifts in the chemical composition of deep water. The climate consequences of those past shifts were severe. They happened before humans were industrializing anything. They happen because of changes in freshwater input to the North Atlantic, which is exactly what is happening again now. The concern is that the current has thresholds, points at which the freshwater input becomes large enough that the sinking in the North Atlantic shuts down faster than the Gradual Models project. Once that shutdown reaches a certain depth, it may become self-reinforcing. Warmer surface water fails to sink, the warm water stays near the surface in the North Atlantic and melts more ice. More fresh water enters the ocean, the sinking weakens further. The loop accelerates. Whether the current is close to that threshold right now is the central scientific question, and the honest answer from most researchers, the uncertainty is real. But the April 2026 study, by showing the weakening as already outpacing model projections, shifted the weight of that uncertainty in an uncomfortable direction. The debate matters practically, because the two scenarios demand completely different responses. Gradual weakening allows for adaptation planning over decades. A tipping point scenario demands immediate and aggressive action to reduce the freshwater input, which means reducing the emissions that are melting the ice on a timeline that is much shorter than current policy frameworks assume. What both camps agree on is that the current is weakening. Both agree that the consequences are serious. Both agree that the trend line is moving in the wrong direction. Where they differ is on how much time remains before the consequences become severe enough to overtake humanity's ability to respond. And buried in both scenarios is a historical precedent that made the whole debate feel far less abstract. Every time a major drought hits the United States, the same debate begins. Is this natural variability, or is this climate change? The question sounds like it has a clean answer. It doesn't. And for the drought spreading across America in 2026, the answer was particularly uncomfortable because the most honest response was both. And both are terrifying for different reasons. Natural climate variability has always produced droughts. The Bermuda High shifting westward, the La Niña pattern in the Pacific cooling ocean temperatures and drying out the south, seasonal temperature swings that accelerate soil moisture loss. These are real, understood mechanisms that have driven droughts for as long as the climate has existed. The 1930s Dust Bowl had natural variability woven through it, alongside the damage done by poor land management. A drought driven by natural variability is, in some ways, a bounded problem. It ends, the pattern shifts, the rain returns, the land recovers. The timeline might be painful, spanning years, but there is a return to baseline. A drought driven by a permanently weakening ocean current is a different category of problem. If the Atlantic meridional overturning circulation continues to slow, the storm tracks that deliver rainfall to the American southeast shift over years and decades, not seasons. The baseline itself moves. There is no return to what normal used to be, because what normal used to be was defined by an ocean current that no longer operates the same way. For the 2026 drought, the scientific picture was genuinely mixed. The immediate proximate cause was the Bermuda High behaving in a way consistent with natural variability, amplified by warmer baseline temperatures from climate change. The role of the weakening current in setting up the conditions for that amplification was real but difficult to quantify precisely in a single season. What scientists could say with confidence was that a warmer, fresher North Atlantic, driven by melting ice and a weakening current, shifts the probability distribution of events like the 2026 drought. It doesn't cause any single drought the way a broken pipe causes a flood. It makes severe droughts more likely, more intense, and longer lasting across certain regions, including the American Southeast. That shift in probability is what makes both answers terrifying. The natural variability answer, if correct for 2026, still operates inside a system that the weakening current is tilting in a darker direction. Even if the rain returns this time, the next dry spell will arrive on ground that is already stressed, aquifers that are already depleted, and a climate baseline that is already drier than it was 30 years ago. The current answer, if it is already influencing rainfall patterns as significantly as some researchers argue, means the southeast may be entering a multi-decade shift toward drier conditions, not just a bad season. Either way, the land and the people on it face a future with less water than the systems built around them were designed for. And the past offered one deeply unsettling look at what a truly weakened current could do to the world. About 12,000 years ago, the Earth was warming out of the last ice age. Glaciers were retreating, sea levels were rising, temperatures across the northern hemisphere were climbing towards something resembling the climate of today. The transition was underway. And then, over a period that geologists measure as very brief by the standards of planetary history, it stopped. Temperatures across the northern hemisphere plunged. Europe, which had been warming, dropped back into near-glacial cold within a century, possibly within decades. Glaciers that had been retreating began advancing again. Forests that had been expanding north. The warming that had been building for thousands of years reversed so quickly that the evidence shows up as a sharp, clean line in ice cores drilled from Greenland. This event lasted roughly 1,300 years. Scientists call it the Younger Dryas. The cause was an enormous flood of fresh water into the North Atlantic. As the glaciers melted, a massive lake of fresh melt water had been building up behind an ice dam in what is now central Canada. When that dam broke, somewhere between 12,000 and 13,000 years ago, it released a volume of fresh water, roughly the size of the Black Sea, into the North Atlantic in a geologically short burst. That fresh water diluted the salinity of the North Atlantic surface layer. The sinking that drives the Atlantic meridional overturning circulation slowed dramatically. The heat that the current normally carries north stopped arriving. Europe went cold. The monsoon systems that water Africa and Asia shifted. Droughts intensified across large portions of the globe. The sudden climate shift put pressure on human populations that were just beginning to develop early agriculture. 1,300 years of disrupted climate from a single pulse of fresh water. The fresh water entering the North Atlantic today is coming from a different source. Greenland's glaciers are melting continuously rather than all at once. From a catastrophic dam break, the rate is slower than the Younger Dryas event, but the cumulative volume is significant and growing. The ice sheet continues losing mass, the meltwater continues flowing into the ocean. Scientists who study the Younger Dryas do not claim that a repeat of that event is imminent or certain. The climate system today is different in important ways. Greenhouse warming is adding heat to the system that the Younger Dryas world didn't have to contend with. The current slowdown would be competing against that background warming rather than occurring in a cooling world. But the Younger Dryas demonstrates something that the models and the data confirm. The Atlantic circulation is capable of rapid, dramatic change when freshwater input crosses certain thresholds. It has done it before. The consequences when it happened were civilizational in scale. The question scientists are now asking is how close the current influx of fresh water from Greenland's melting ice is to a threshold that could trigger a similarly abrupt response. The honest answer is that nobody knows exactly where that threshold sits. But the direction of travel is clear, and the consequences of approaching it were already becoming visible in storm tracks, rainfall patterns, and drought footprints across the northern hemisphere, including the one spreading across the American southeast in the spring of 2026. Rain arrives at a particular place because a storm tracked over it. Storm tracks are the paths that weather systems follow as they move across continents and oceans. They are not random. They follow channels carved by large-scale atmospheric patterns, the same way rivers follow valleys carved by water over time. These channels are shaped by temperature differences between the ocean surface and the atmosphere above it, by the position of the jet stream, and by the circulation of heat and moisture that the Atlantic current drives. Change the current, and you change those channels. As the Atlantic meridional overturning circulation weakens, the temperature contrast between the North Atlantic and surrounding regions shifts. The North Atlantic cools relative to where it was. The jet stream, which sits at the boundary between cold polar air and warmer subtropical air, responds to that cooling. Research suggests the jet stream shifts and becomes more variable as North Atlantic temperatures change, sometimes plunging south in dramatic cold air outbreaks, other times lifting far north and allowing warm air to penetrate deep into the Arctic. For the American Southeast, the most significant projected shift in storm tracks is a tendency for moisture-carrying systems to track further north than they historically have. Instead of rain systems pushing into Georgia and Florida, they ride the altered jet stream into the Carolinas, Virginia, and the Northeast. The Southeast, already in the lee of the Bermuda High when it strengthens, receives less of the storm track moisture it historically counted on. This is not speculation built on one model. Multiple independent climate modeling groups, using different approaches and different data sets, project a similar pattern. The details vary, the magnitude varies, the timing varies, but the direction of the shift, drier for the southeast, is consistent across a broad range of projections. For cities like Atlanta, which draws its water from a single reservoir system that depends on predictable rainfall, a multi-decade shift toward drier conditions in the southeast is an infrastructure crisis in slow motion. The city came within weeks of running out of water during a severe drought in 2007. The population has grown considerably since then. The water system has expanded, but the underlying rainfall it depends on is trending in the wrong direction. For agriculture across the Gulf states, which produces enormous volumes of peanuts, cotton, broiler chickens, and specialty crops, a shift in storm tracks translates directly to changes in where and how much farming is viable without irrigation. Irrigation at scale requires either surface water or groundwater. Both are already under stress. The irony of the storm track shift is that some regions would see more intense rainfall from the redirected storms, even as the annual totals shift. A storm track that brings more moisture to New England could also bring flooding to areas that are not built for it, while the southeast bakes, more rain in some places, less in others. The same water moving through a different pattern, driven by a changing ocean current that most people had never heard of until scientists started publishing alarming findings in the spring of 2026. The question of whether any short-term weather pattern might interrupt the drought still had one candidate. Scientists and farmers alike were watching a familiar phenomenon forming over the Pacific. It was called El Niño, and the hopes riding on it were complicated by the science. Every few years, the Pacific Ocean runs warm. A band of unusually warm surface water spreads across the central and eastern tropical Pacific, disrupting the normal patterns of wind and rainfall across the globe. This warming event, called El Niño, has predictable effects on large portions of the world. It suppresses rainfall in Australia and Southeast Asia. It brings unusual warmth to the western coast of South America. And for the United States, it typically brings wetter and cooler conditions to the Gulf states in the southeast during the winter and spring months following its peak. In the context of the 2026 drought, El Niño was being watched as a potential circuit breaker. A strong El Niño developing over the tropical Pacific could shift storm tracks southward across the United States, pushing moisture into the drought zone and providing the prolonged rainfall the region desperately needed. The problem was the uncertainty surrounding both the El Niño itself and its interaction with the drought's deeper causes. Climate forecasters in spring of 2026 were tracking conditions in the Pacific that suggested a moderate El Niño event was possible over the following months. Possible, not certain. El Niño events are notoriously difficult to predict more than a few months in advance. A pattern that looks like developing El Niño conditions in April can fade out by June or intensify beyond what early signs suggested. Even if a moderate El Niño did develop, its effects on the southeast drought were not guaranteed. El Niño's rainfall signal in the southeast is strongest in winter and spring. By the time a developing El Niño reached its peak, the window for its most useful rainfall effect might have already passed. Summer rains in the southeast respond less consistently to El Niño than winter rains do. And there was a deeper problem. El Niño can bring more rain, but it cannot refill aquifers. A single wet season, even a very wet one, would not reverse the structural damage the drought had done to underground water reserves, eroded soils, and depleted river systems. Scientists estimated that even with an aggressive return to above-average rainfall, the Floridan aquifer alone would need years of above-average recharge to return to pre-drought levels. The drought had also built its own momentum through a feedback process that El Niño could slow, but not immediately stop. Dry soil reflects more sunlight back into the atmosphere than wet soil does, which warms the air above it and accelerates evaporation, which keeps the soil dry. This feedback loop, once established, resists breaking even when rainfall increases modestly. El Niño was a hope, a real one, with genuine scientific support behind the possibility of rainfall relief. Farmers watched the Pacific forecasts carefully. Water managers built contingency plans around different El Niño scenarios. But it was not a solution to what the drought had already done, and it was certainly not a solution to the ocean current slowdown driving the longer-term shift in rainfall patterns. For that, the problems ran far deeper than any single weather pattern could reach. Literally, some of the deepest damage from the 2026 drought was buried underground, in aquifers and soil layers that would take decades to recover, regardless of what the Pacific Ocean did next. When a river runs low, rain can refill it in a season. When a reservoir drops, a wet winter can bring it back. Surface water responds to precipitation relatively quickly. Rain falls, water flows downhill, lakes and streams fill up. The connection between rain falling and surface water recovering is visible, measurable, and often achievable in months. Underground water operates on a completely different timeline. An aquifer is recharged by water that falls on the surface, soaks through soil, filters down through rock, and eventually reaches the saturated zone where the aquifer holds its water. This process is slow. In a healthy system with good soil conditions and regular rainfall, recharge might add a few inches of water depth to the aquifer each year. In some deep aquifer systems, the water being pumped today fell as rain hundreds or thousands of years ago. When an aquifer is drawn down by drought and heavy pumping, reversing that deficit requires years of above-average rainfall, combined with reduced pumping, years during which communities still need water. Farms still need irrigation, cities still need drinking water supplies. The Floridan aquifer is a relatively fast recharging system by geological standards. Its porous limestone allows water to move through it more quickly than many other underground systems. Even so, recovering the deficit created during the 2026 drought was projected to take several years of above-average rainfall, assuming pumping demand returned to pre-drought levels, which was not guaranteed given population growth. The Ogallala Aquifer, which sits under the high plains from South Dakota down to Texas, and irrigates roughly 30% of all groundwater irrigated farmland in the United States. Much of the Ogallala was filled during the last ice age. The annual recharge rate across most of it is measured in fractions of an inch. Farmers have been drawing it down for decades at a rate that far exceeds recharge. In some areas, they have already pumped through 80% of what was there. When those sections run dry, they will not refill in any human time frame. The 2026 drought accelerated Ogallala depletion in the same way it accelerated Floridan depletion. The drought reduced surface water availability. Farmers turned to groundwater. The aquifer dropped faster. The physical changes inside an aquifer during overdraft compound the recovery problem. When water is pulled out of limestone or sandstone faster than it is refilled, the rock structure can compact. This compaction is sometimes irreversible. The pores and cracks that held water collapse under the weight of the rock above. Even if water returns, it cannot fill spaces that no longer exist. The total storage capacity of the aquifer permanently decreases. In certain areas of California, land subsidence from aquifer compaction has caused the ground surface to drop by feet over decades. Wells that were drilled to a certain depth now reach only to empty rock. Infrastructure built on the assumption of a stable ground surface has cracked and shifted. The 2026 drought added a new layer of urgency to a problem that had been building for years. It was not the start of America's groundwater crisis. It was an acceleration of it, and the rain, whenever it returned, would find a landscape that had changed in ways that would make future droughts worse even if the next season was wet. Every major American city was built on an assumption that the water would keep coming, that the river would keep running, that the rain would fall roughly where and when it always had, that the aquifer below the city would stay full, that the infrastructure built around those assumptions, the pipes, the treatment plants, the reservoirs, the canals, the dams, would remain adequate for the population depending on them. The 2026 drought exposed how fragile that assumption had become. Atlanta is one of the clearest examples. The city and its sprawling suburbs rely almost entirely on surface water from a single river basin, the Chattahoochee, and the reservoirs it feeds. During the 2007 drought, a federal court fight over water rights with Alabama and Florida, both of which also depend on the same river system, brought Atlanta within weeks of running out of usable water. The population of Metro Atlanta has grown by over 1 million people since then. The city has improved its conservation programs and added some storage capacity, but the fundamental vulnerability remains. A river system shared by 3 states, each with legitimate and growing claims on the water, with rainfall patterns that may be shifting due to changes in storm tracks tied to the Atlantic circulation. The margin is thin, and the population keeps growing. Phoenix and Las Vegas built entire metropolitan identities around the desert. Both cities depend heavily on the Colorado River, which has been running below the level needed to meet all the demands placed on it for years. Water from the river is diverted across hundreds of miles of canal systems to reach these cities. The drought of 2026 reduced Colorado River inflows further, and the reservoirs that store that water dropped to levels that triggered shortage declarations affecting millions of people. Miami is a different kind of vulnerable. It sits on porous limestone just feet above sea level. Its drinking water comes from a shallow aquifer that sits just below the ground surface. As sea levels rise and the aquifer drops from drought-driven pumping, the vulnerability grows from 2 directions at once. Salt water encroaches from below as the ocean rises. The freshwater supply diminishes from above as drought reduces recharge. Houston, which sits in a region that should receive abundant rainfall, has seen its distribution become more erratic. Extreme flooding alternates with dry periods of increasing intensity. The city's water infrastructure was designed for a certain pattern of rainfall distribution. That pattern is changing. The water systems of American cities were engineered generations ago. They are expensive to rebuild. The political process for approving large infrastructure investments is slow, and the climate is changing faster than the planning cycles that govern infrastructure decisions. The drought made these vulnerabilities visible in a way that individual wet or dry seasons had not quite managed before. Because the 2026 drought wasn't just one bad year layered on top of a stable system, it was one bad year layered on top of decades of gradual depletion, arriving in a climate where the conditions that had made the original infrastructure assumptions reasonable were no longer guaranteed. The feedback loops underneath all of it, the mechanisms that made dry conditions self-reinforcing rather than self-correcting, were the hardest part of the picture to look at clearly. Drought does not simply end when rain returns. It leaves behind a landscape that is more vulnerable to the next drought than it was to the one that just passed. The mechanisms are physical, chemical, and ecological, and they compound over time in ways that make recovery progressively harder. Start with the soil. Healthy soil holds moisture through a combination of organic matter, a network of roots and fungi, and a structure full of tiny pores and channels built by earthworms, beetles, and other soil organisms over years. This structure allows rain to soak in efficiently rather than running off. During a severe drought, soil organisms die. Root networks collapse as plants die back. The organic matter that holds soil structure together dries out and breaks down faster. The surface of the soil crusts over, sealing the pores. When rain eventually falls on this compacted, crusted surface, it runs off rather than soaking in. The aquifer below receives less recharge. The streams fill briefly and flash, then dry again. The rain that came to end the drought contributes less to actual water recovery than the same amount of rain would have contributed to healthy soil before the drought. The vegetation on the surface compounds this problem. Native grasses and deep-rooted plants that anchor soil and channel water downward into the ground were stressed or killed by the drought. The plants that grow back first tend to be shallow-rooted opportunists, less effective at holding soil, less effective at funneling rain into the ground, and more vulnerable to the next dry period. The fire damage across the southeast in 2026 added another layer. Fire burns the organic matter in soil, leaving behind a hydrophobic layer, a layer that actually repels water just below the surface. Rain falling on burned ground in the months after a fire runs off at very high rates, carrying topsoil with it into streams, clogging river systems with sediment, and contributing almost nothing to groundwater recharge. At the larger scale, the drought changed the reflectivity of the land surface across an enormous area. Dry, bare soil and dead vegetation reflect more sunlight back into the atmosphere than wet green land does. This reflection warms the atmosphere directly above the dry area. That warmer air is drier and less likely to produce rain. The drought, by killing vegetation and drying the soil, actively reduced the probability of rain in the region where rain was needed most. Climate scientists call these mechanisms land-atmosphere feedbacks. They are well documented in the research literature. They are one of the reasons that droughts in certain regions, once established, tend to persist longer than a simple weather pattern would predict. The land itself, damaged by the drought, acts to sustain the dry conditions. The 2026 drought was burning these feedbacks into the southeast's landscape in real time. Recovery, when it came, would be slower than any historical average suggested, because historical averages were built from conditions in which the soil, vegetation, and atmosphere were starting from a healthier baseline. And this feedback problem was only going to be amplified as the longer-term shift driven by the weakening ocean current continued to push rainfall patterns away from the region. The scenario that scientists described when they tried to put all of these pieces together had a name, and the threshold it described was unlike anything in modern human experience. A tipping point is the moment a system stops recovering and starts accelerating in a new direction. Push a ball up a hill, and it rolls back down toward you. That is a stable system. Push it over the top, and it rolls away from you, faster and faster, toward a completely different place. That is a tipping point, the moment the direction of travel changes permanently. Climate scientists believe the Atlantic meridional overturning circulation has a tipping point, a threshold of freshwater input and temperature change, beyond which the sinking in the North Atlantic weakens so dramatically and so quickly that the current shifts into a fundamentally different and far weaker state, a state it may maintain for centuries before recovering, if it recovers at all, on any human timescale. The evidence for this tipping point comes from multiple sources. The paleoclimate record, meaning the history of the climate written in ice cores and ocean sediments, shows that the circulation has tipped before. The Younger Dryas event, the sudden cold snap 12,000 years ago, appears to have been exactly this kind of tipping point crossing. The current didn't weaken gradually over centuries, it collapsed rapidly and stayed collapsed for 1,300 years. The physics of the circulation supports the possibility. Researchers working with mathematical models of the ocean can construct scenarios in which the freshwater input crosses a critical level and the sinking shuts down in a nonlinear way, meaning far faster than a simple projection of the current slowdown rate would suggest. The debate in the scientific community is not about whether this threshold exists. Most researchers accept that it does, based on the past record. The debate is about where that threshold sits relative to where the current is today. How much more freshwater input would it take? How much more weakening Is the circulation still far from the threshold, giving humanity decades to reduce emissions and slow the melt? Or is it already close, meaning the meltwater already committed from the ice that has already started flowing could push it over without any additional warming? The April 2026 studies finding that the weakening was occurring 60% faster than models predicted shifted this debate in a specific direction. The models that placed the threshold far away were also the models that had underestimated the weakening rate. The models that placed the threshold closer were the ones whose projections better matched the observed data. This does not mean collapse is certain or imminent. The range of scientific opinion remains wide, but the weight of recent observational evidence has moved the probability distribution. The scenarios scientists once considered unlikely have become scenarios they now consider possible within this century. The day the current crosses its tipping point, if it does, would not look dramatic from the surface. No alarms, no visible change. The ocean would look the same. The currents would still be moving, but the deep sinking would have slowed past the point of self-maintenance, and the trajectory would have changed. The rainfall patterns, the storm tracks, the European temperatures, the coastal sea levels, all of them would be committed to a new equilibrium. And the southeast of the United States, already in the grip of its worst spring drought in over a century, would be looking at a future where the conditions of 2026 were not the exception. They would be the new baseline. Scientists are careful with prediction. They speak in probability ranges, confidence intervals, and scenario families. They are trained to hold uncertainty honestly and to avoid overstating what the data supports. But when researchers who studied the Atlantic circulation, the American drought record, and the feedback loops connecting them are asked directly what the next decade looks like for the Southeast, the answer that comes back, stated carefully but clearly, is harder than the last one. The convergence of pressures on the Southeast is unusual in its breadth. The weakening ocean current is shifting storm tracks northward over a multi-decade time frame. The baseline temperature of the region has risen by roughly 2 degrees Fahrenheit over the past 50 years, which increases evaporation and makes every dry period more intense. The aquifers that buffered previous droughts have been drawn down significantly. The Everglades, which regulated the water cycle for southern Florida, is damaged. The soil across millions of acres of agricultural land is compacted and depleted of organic matter from the 2026 drought event. Each of these pressures compounds the others. Warmer temperatures on stressed soil make drought establish faster. Depleted aquifers provide less buffer when drought arrives. Damaged land surface feedbacks make drought persist longer once established. A weakening current makes the large-scale atmospheric setup for drought more common. The projection for agricultural viability in the Southeast over the next decade includes a significant increase in the frequency and severity of growing season droughts. Farmers who currently make irrigation a seasonal supplement may find it becoming a year-round necessity. The crops they grow may need to shift toward more heat and drought-tolerant varieties, which in many cases means lower yields and lower market value. Water conflicts between states that share river systems are expected to intensify. The legal frameworks for allocating water in the eastern United States were written when water felt abundant. They were not designed for sustained scarcity. Federal courts have already been asked to adjudicate competing claims on shared river systems. The caseload is expected to grow. Cities in the region face a decade of increasing infrastructure investment requirements, flood protection from rising seas on the coast, water storage capacity inland, wastewater systems that can handle more intense but shorter rainfall events. All of this requires capital expenditure that competes with other public priorities in economies already stressed by agricultural losses and insurance premium increases. The insurance industry is already adjusting. Property insurance in Florida has become some of the most expensive and difficult to obtain in the country, driven by hurricane risk and flooding. The addition of persistent drought risk, wildfire exposure, and water supply uncertainty adds further pressure to insurance markets. When insurance retreats from a region, property values follow. When property values fall, the tax base that funds public water infrastructure and emergency services shrinks. The next 10 years will not look like a single dramatic collapse. They will look like a series of bad seasons, each a little worse than the last, separated by brief recoveries that feel like improvement, but don't quite reach the baseline the one before them started from. Unless something changes at the source of the problem. The drought gripping the American Southeast in 2026 had multiple causes operating at multiple scales. At the smallest scale, individual water use decisions. At the regional scale, land management practices that either protect or damage the soil's ability to hold and channel water. At the national scale, the emissions driving global warming and the policy frameworks governing how water is allocated and protected. At the global scale, the rate at which ice continues to melt and fresh water continues to enter the North Atlantic. Each scale offers real actions, and each scale has a closing window. At the individual level, the most effective actions are less dramatic than they sound. Reducing outdoor water use during drought is measurable and immediate. Supporting water-efficient landscaping in residential areas reduces municipal draw on stressed aquifer systems. Choosing foods from drought-adapted agricultural systems, where consumer pressure actually influences how farmers use water, moves money in a direction that matters. At the municipal and state level, the most urgent need is investment in water system redundancy. Cities like Atlanta, which depend on single-source water systems, face catastrophic risk when that single source fails. Diversifying water supply, whether through desalination on coasts, expanded water recycling, or regional sharing agreements, reduces the brittleness of systems built on assumptions that no longer hold. Managed aquifer recharge programs, which actively direct treated water back underground during wet periods, can help rebuild reserves that drought has depleted. Land management offers some of the fastest-acting solutions. Restoring wetlands along river systems allows those wetlands to store water during wet periods and release it slowly during dry ones, functioning as the natural buffers that draining and development removed. Restoring native vegetation on agricultural land that can no longer support economically viable crops reduces the land surface feedbacks that help drought sustain itself. Prescribed burning programs conducted during safe conditions reduce the catastrophic fuel loads that turn drought conditions into firestorms. At the national level, the emissions trajectory is the lever that connects most directly to the Atlantic circulation's future. The fresh water entering the North Atlantic comes from melting ice. The ice melts because the atmosphere is warming. The atmosphere is warming because of accumulated greenhouse gas emissions. Every fraction of a degree of warming that is avoided through emission reductions reduces the rate at which ice melts, which reduces the rate at which fresh water dilutes the North Atlantic, which slows the weakening of the circulation. This connection is real and scientifically grounded. It is also slow. The emissions reduced today affect temperatures a decade or more from now, and the ice sheets and ocean circulation respond on even longer timescales. The current that is weakening today is responding to warming that happened years and decades ago. There is no action that reverses the situation this year or next. But there is a difference between a circulation that weakens to 50% of its historical strength and stabilizes, and one that weakens past its tipping point and reshapes the climate of the Northern Hemisphere for centuries. That difference is measured in emissions, in decades, and in the decisions made now while both outcomes are still possible. The spring of 2026 showed the American Southeast what a weakened, drought-prone future looks like. On the ground, the cracked fields, the burning wetlands, the empty aquifer, the smoke hanging over cities that should have been wet. That picture is not fixed, but the window to change it is smaller than the models assumed and closing faster than the plans were built for. The current is still moving. The question is how much longer it can carry the weight of the climate that billions of people depend on. And the answer depends on decisions being made right now.